Alrighty, so we're going to just kind of qualitatively cover Chapter 5 before moving into Chapter 8, because Chapter 5 should essentially be review for you from Physics 280 and possibly also Physics 380 if you've had quantum mechanics, Physics 380. But we certainly need to remind ourselves about how all this works because it's so important in astronomy. So first of all, we have what are called Kirchhoff's laws. You may not have seen them as Kirchhoff's laws per se, but they're kind of the rules that spectra follow, the different kinds of spectra that we might see. And so if you have a hot light source, so that could be, say, the filament of a light bulb, an old-fashioned light bulb, or it could also be a hot liquid or a hot dense gas, then you will see a continuous rainbow spectrum that, to the extent that it is well described by the ideal thermal spectrum, blackbody spectrum, it'll be a Planckian spectrum, and that's what that curve here would be part of. So the light bulb produces light of all visible wavelengths or colors, and so here's a plot of intensity versus wavelength, B lambda versus wavelength, or F lambda versus wavelength. And you just see a continuous rainbow if you were to spread it into a spectrum. Well, how would you do that? Well, one way is to pass the light through a slit and then allow that slit of light, to that narrow shaft of light, to pass through a prism to spread it into all of its component colors. Or you could use a diffraction grating like one of these, which has many parallel lines ruled into it, and then light scattering off of those grooves interferes. You get a diffraction grating. These have 1,000 lines per millimeter. So the lines on these are a micrometer apart, a micron apart, and I'll have you look at some spectra in a minute by holding it up to your eye. Have you folks used these things before? How many of you have never used one of these before? So we will do that anyway again, because you know you can just never run out of opportunities to see things again. And so I'll switch on the hydrogen lamp there, and then also you can yeah, you get a decent, almost continuous spectrum out of the fluorescent lights, so you can look at those too. On the other hand, if you have a low-density gas, the atoms in a warm gas cloud emit light only at specific wavelengths, and those are determined by the cloud's composition and temperature. In other words, as you know, atoms like to emit very specific wavelengths, and every element has its own particular set of spectral line wavelengths. And so again, what you're really seeing when you see spectral lines would be you've got a slit there, and the spectral lines are just images of the slit at the different wavelengths that that cloud of gas is emitting. Or if you got yourself one of these, a tube full of hydrogen that has 5,000 volts placed on the two ends, so that a current flows through and ionizes the hydrogen, and then electrons recombine with protons that have had their electrons stripped away, drop down the energy ladder, why you can get visible light as a result of that. And so here is a hot cloud of gas, and I'll have you come up in a few minutes and put this in front of your eye, and what's happening here is that the diffraction grating is spreading the light into all the component colors, and then the lens of your eye is focusing the pattern onto your retina so that we don't need a slit. We don't need a slit here because the tube itself is a narrow shaft of light already, and so you'll see a bunch of images of the tube at the different wavelengths that it likes to emit. And then the other situation is when you have a cool cloud of gas in front of a hotter light source. Actually, the cloud of gas doesn't really have to be cool, it just has to be lower temperature than the hot light source, the hot source of continuous spectrum behind it. And then atoms in the gas cloud will selectively absorb the same wavelengths that they like to emit. If they don't have something behind them and you're just looking at the light that they emit, well, they absorb those same wavelengths as well. And so you get dark lines in the spectrum, and we will talk in much more detail about that soon. It's more complicated than this makes it sound in the end, determining how dark the spectral lines will be and so forth. But anyway, simplest picture is to think of the atoms absorb some of the light coming from the hot light source, and you get a series of dark lines. Now, once they absorb light, electrons can jump down energy levels again and emit light as well. And so you might think, well, why don't the photons just get replaced? And that's because when the atoms emit light, they'll emit it in some random direction. And so as a result of that, the light has been, in a sense, scattered out of the beam by the atoms absorbing photons and then spitting them in a direction that typically isn't going to be in the same direction that the beam of light was traveling. So I think it's a good idea to see these things for yourself. So I'm going to hit the lights here, and everybody's going to come up and borrow one of these diffraction gratings from me. Be sure you hold it in the right orientation. In other words, you should be able to read the words. Normally, if you hold it like this, the spectrum will go that way, and you won't be able to see it very well. So come on up. It's a field trip. Woo! So let me hit the lights here. I'll be violent and hit all off. There we go. So do like me, hold it up to your eye, and what you should see is a lovely red line, a lovely turquoise line, a lovely line which I'm going to choose to call bluish purple. Some might call it indigo, but I won't. And there's another one there that you probably won't see. There's two very kind of deep purple bluish lines, but the other one's pretty dim. So indeed. And for you. Thank you. And for you. And of course, the proper terminology here is ooh, ah, right? So there we go. And there we go. Yes. Ooh, ah. If you look at the screen, you'll see the RGB. You'll see they'll be all spread out because you're looking at the whole screen there, but you know, there's...
Is there to orient it?
What's that?
Is there to orient it?
Yes, there is. The wording should be horizontal.
Okay.
Yes. Yes, yeah. So you should see on either side, right? If you look straight at it, you just see all the colors coming from the tube, and it looks the pinkish color. But if you look to either side, you will see spectra on both sides of it. Because the grooves scatter light in every direction, so you'll get constructive interference for different wavelengths at different angles from the central axis. So you'll see a copy of the spectrum on both sides. And you should see a very deep and lovely red line, a deep and lovely kind of teal or turquoise line, and a deep and lovely bluish purple line. Yes. And if you're really good, you might, yes, CJ.
I was going to say, why is it that like even when I get it out of my line of sight, I can still see it over there?
Because you're still seeing the light scattered towards you by the diffraction grating. In other words, light's coming towards the diffraction grating, and it's scattering different wavelengths at different angles. And so it's entirely possible you're looking this way, light hits it, and then gets scattered towards your eye that otherwise would have gone straight through and not come to your eye. So yeah, you don't have to be looking right at it in order to see it. And in fact, if you look very far off to the side, you might start to see, I'm not sure with these of you or not, the second order. There's actually multiple orders. What you'll see most readily is the first order spectrum, where between each successive groove, there is one wavelength of path length difference. But you can also see potentially a second order spectrum further away, where there's two wavelengths of path length difference, and so on and so forth.
You can barely get the second order.
Yeah, it's kind of hard. Yeah, because way over there, yeah, because these are fairly closely spaced, and so they do spread it out quite a bit. Oh, you took a picture of it? Oh, cute. So that's the first order line right there.
How do you say which is the second order?
It will be way over to the side, so you're not likely to capture it easily with these. I don't think I might have some ones that only have 500 lines per millimeter, and with those you'd be more readily able to see that. Yeah, with these, I think the grooves on these, I think the lines are further apart from one another, closer together. No, further apart, and so they don't spread out the spectrum as much. Yeah, so try these, you'll be able to see the second order spectrum more readily. So I'll trade you, and if you look off to the side, you can pretty readily see, oh, look, another copy of the red line, another copy of the teal line, and so forth. So yeah, I'll get these from you, and then trade you with the ones that have probably only 500 lines per millimeter instead of 1,000 lines per millimeter. So they're
going to look directly into the sun then.
look directly into the sun. Yes, we actually are going to look at the solar spectrum in a minute too. So, all right, here have some not as dispersive gratings here. And these you might have to, it's not as obvious which way to orient it. So if you don't see the spectral lines on the side, rotate it 90 degrees. Did I give you one? Yeah, okay, yeah.
Thank you.
Yeah, with these it should be easier to see the second order spectral lines.
Oh, yeah, I see them.
Yep. Yeah, so you see two copies of all the spectral lines with these. Yeah.
Can hold it up in front of the camera so that people on the video can...
No, they don't get to see it. I actually have a video which I made of me holding up a diffraction grating to, I'll show that for the people on the video here. So let me, I will escape here and go to my YouTube channel here, which is just my OBU YouTube channel. So let's go to YouTube. YouTube. And be signed as me. Are you signed in as me? No? Yes, you are? And I do prefer to be in dark mode. Now I can't read it very well. Where's the appearance? Dark theme. And I'll go to my channel here. It's so hard to see it here. Let's see. Because I have YouTube Premium. Oh yeah, view my channel here. And yeah, these are videos where, oh look, it's rotating stars. Let's see, videos. Did I tell you the story of this? So I made these videos for precisely this reason. And then my wife made fun of me because it's kind of like Jaws with the shark sneaking up. And then this person in the Netherlands contacted me and asked if he could use my video for these educational videos that they're making. And so as a result, I have several hundred views of these things. So yes, let's see. Oh, let's start with a continuous spectrum here. This one doesn't have as many views. It's not as exciting. But here we go. So, all right. Do 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 do. Yeah, my wife just thinks this is hilarious there. Ooh, continuous spectrum on either side. Ooh, ah, right. And then let's see.
Imagine driving with Lisa's glasses.
Yeah, right. And then cozy jazz. That's probably. Wow, there we go. Isn't that nice? I've been playing. You know, I used to listen to a German radio station to go to sleep, but the news is so upsetting. It's even upsetting in German. So I play this music to help me fall asleep instead, like like nocturnes and stuff like that. So, all right, go backwards and get to, let's see, the one that's most popular would be the, my videos again. Oh, look, it's videos for like astronomy there. The hydrogen spectrum, how many views has this one got now? It's like 840 something or something like that? Yeah. How many? 842. 842, okay, so here we go. Let's get this one going here. Once again, JAWS. Doo-doo. Do 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 and woo, ah, yes, glorious. And the not as popular, and yet still relevant. Stop it! Don't do that. No, that's it. What, oh, entropy. Oh, that's a good video. I think it's a Veritasium video, right? Yeah. But let's look at helium, which I could bring out a helium lamp here, but I won't because you'll just enjoy this view instead. Stop it. Okay. Oh, jeez. Okay. Where's my channel again? Where do we go here? Oh, she's pretty entertaining. I think she's Australian, and she's pretty funny. Anyway, let's see. Where's my channel? It's so far away over here. I'll view my channel. View my channel. Okay, and now let's look. Come on. Oh, videos. Got to hit videos. Videos. And helium. Helium. All right, here we go. Do. Whoa! Look, it's different wavelengths. Ooh. Ah. Yes. Whereas my videos about how to use ASTR Image J, one of them's got like what, something like 7,000 views or something, 5,000, 7, I forget. Anyway. So I get the impression either amateur astronomers are learning how to use ASTR Image J. Yeah, oh, these are fun, these night drives in Tokyo and stuff like that.
We use them to study.
Yeah. This is like, there's this, it's like ABA, like a bow vision or something like that. It's like lo-fi beats. I'm like, oh, this is totally chill. I'm enjoying this, yes. Right, but not right now, okay. So, and what did I do? Did I manage to do a tab stack by accident? Okay, all right. There we go. Now, next up, let's see ourselves. Well, let's see. Well, we'll do it in a few minutes. Okay, so sit down. Well, bring me the things back again here.
May I have one of these?
Yes, you may. As a matter of fact, yes. Help yourself. Alrighty. Thank you. I guess I'll put these away later. Thank you. Okay. And so, every chemical element has its own unique set of spectral lines, right? Every element has it. I hit all off again. All on. Every element has its own unique set of spectral lines. You know why, but we're going to review that in a minute. No, not you stupid can lights. Although they're great for a continuous spectrum, I will say that. You get a nice rainbow with them. Can lights. The can lights. Right? So, all right. And the spectral lines of an element are the same wavelengths for both emission and absorption. And we can look at the sun spectrum. It has an absorption line spectrum. By matching spectral lines in the sun spectrum with a laboratory spectra, we can determine the composition of the sun. We don't have to go take samples. We can spread the sun's light into a spectrum and match it up with spectra that we observe in the laboratory. So here is a laboratory spectrum below an emission line spectrum of iron, so hot iron gas heated up to produce emission lines. And if you look at the top, you can line them up one for one with a series of the dark lines in the sun spectrum. So we know the sun contains iron. The sun is so freaking hot, that's the technical term, that everything's a gas. And so the sun contains gaseous iron and praseodymium, and you name it. Praseodymium is my favorite name for an element. I like that name, praseodymium. Ytterbium's good too, yttrium, I like those kind of elements like that. Okay. Okay, we'll do that in a minute. Let's go look at, we'll do some other stuff and then we'll have fun talking about the sun spectrum in a few minutes here. And looking at it. So again, you've seen this at a much higher level of understanding, but I'm still just reminding you here. These are slides that basically I would use in intro astronomy. You, of course, know that in the nucleus of an atom, you've got your protons and neutrons. Protons are positively charged, neutrons are neutrally charged, that's why they're called neutrons. And then you have the electrons that are negatively charged. How does the negative charge on an electron compare to the positive charge on a proton? Yeah, they're equal and opposite, so to speak, right? Same magnitude. You also know that electrons do not literally orbit the nucleus like you often see these depictions as though they were planets orbiting the sun, because they're described by quantum mechanics and the Heisenberg uncertainty principle, which says that electrons simply don't have a well-defined position and momentum at the same time. And so, you know, when you solve the Schrödinger equation, that you find that the electrons are described by wave functions that are spread out. They are probability waves, where psi star psi is the probability density, and psi star psi times a little volume element is the probability of finding the electron in some little volume element dV. And you know, well, let's see, can the electrons in an atom just have any old energy that they like? No, they're only allowed specific energies, which we obtain by solving the Schrödinger equation. And so the analogy that this book that I've used in the past makes, which I think is a good one for kind of relating, helping people relate to it, is, you know, if you think of gravitational potential energy, if I pick up this eraser, then the gravitational potential energy relative to some reference is mg times its height above that reference. And classically speaking, I can give it any gravitational potential energy that I like, because I can move it as high or as low as I like. But electrons in the atom ain't like that. If they were described by gravitational potential energy, it would be sort of like books on a shelf, where the book can't be in between the shelves. I mean, yeah, you could hold it there, but in other words, it's more like, well, no, it's got to be on a nice stable shelf. It can't just be anywhere. It's got to be on a nice stable shelf. And so why the bookshelf has quantized the gravitational potential energy of War and Peace there. I like how they chose War and Peace as the example of a book. And we can use energy level diagrams to represent the allowed states of an atom, right? So you just draw horizontal lines that represent the energies of the electrons in the atom that they could have. And so you've got a ground state, and that's by analogy with gravitational potential energy, where the lowest potential energy in this room, at least, that the eraser could have is being on the ground, because you can't just get below the ground now, can you? No, you cannot. So that's the ground state. And then if we had a bookshelf, there'd be a first excited state, and we may call the ground state E sub 1, and the first excited state E sub 2, the next shelf up, shelf above that, E sub 3, E sub 4, and so on and so forth. We're in our energy level diagram. Horizontal lines to represent the different allowed energies coming out of the Schrödinger equation. And you can put a little dot to represent the electron occupying the orbitals that have the relevant energy. And so analogously, atoms exist in one allowed energy state or another, but not in between. And so here's just, you know, kind of hypothetically, here's an atom in an E2 energy state. And so the blue shading represents the probability density of the orbital. And they're not trying to be precise here. They're just kind of qualitatively saying, oh, look, orbital shading. And here's the energy in the E4 state. And it is true that you find that higher energy orbitals are more spread out away from the nucleus. In some sense, the electron is further from the nucleus when it has a higher energy, which makes sense because the electron is negatively charged, the proton is positive, the protons are positively charged. So if you imagine, classically speaking, pulling the electron away from the nucleus, you would have to do work because you'd be pulling against an attraction between them. And so you would be increasing its potential energy by moving it further away from the nucleus. you'd be doing work on it, you'd be increasing its total energy. So it works out in quantum mechanics too, that the further away in an average sense the electron is from the nucleus, the higher its energy will be. But again, there can only be specific energy levels allowed. And then we want to talk about how spectral lines are produced. So here's this mental model that we make for ourselves. So let's talk about some hypothetical atom which only has 2 levels. And with, my humility is just one of my many outstanding qualities. And so I choose to call this hypothetical atom harmonium. So here we have harmonium, and it only has 2 energy levels. E sub 1, its ground state, and E sub 2. A hypothetical atom has 2 allowed energy states with energies E sub 1 and E sub 2. If, for some reason, the electron is in the E2 level, it could be there was a collision with something that gave it the energy to jump up to that level. Or maybe, not shown here yet, it absorbed a photon to get it up to that level. But by hook or by crook, it's an energy level E sub 2. Why, it can spontaneously give up energy and drop down to energy E sub 1. The detailed description, it turns out that it's interacting with the quantized electromagnetic field, but we can kind of think of it as like, things seek their lowest energy, so water wants to roll downhill. So if we anthropomorphize our electron, why, it doesn't like having a higher energy, it just wants to be in the ground state if it can, even though electrons, as far as we know, do not truly have desires. They're not sitting there like, God, it sucks up here in E2. I'd really like to be in E1. But in any case, it's as though it wants to be an energy level E1, and so it can spontaneously, we say, emit a photon, and the photon has to carry off the energy that it has lost, and so it drops from energy E2 down to energy E1 by giving off a photon of energy E sub 2 minus E sub 1. And its wavelength will be hc over E sub 2 minus E sub 1. Do you remember what so h is Planck's constant, c is the speed of light. hc is approximately equal to what in EV nanometers? Do you remember? This should totally be burned into your brain. Every astrophysicist should know what hc is in EV nanometers. Yes?
I'm not confident, but it's like 4.2.
Oh, dang it. Nope, dang it. But I appreciate the effort.
It's 1247 something.
So if only you'd stop before you said 7, it's 1240.
Oh.
Yeah, it's 1239 point something, but we're just going to say 1240 EV nanometers. Burn that into your brain. HC is 1240 electron volt nanometers. Right, 1240 electron volt nanometers, which is, it makes calculations easy, right? So if I have a photon whose wavelength is 620 nanometers. Question, could you see that photon? Well, not just one of them, but if you were flooded in 620 nanometer wavelength light, photons coming into your eye. Could you see those photons? Yeah, because it's in that range of, what's the visible spectral range? 400, 700. So 620, take a guess as to what color your eyes would see that as.
Red.
Red, yeah, so that would be a red spectral line if you ever bathed in photons of 620 nanometers wavelength. What's their energy in electron volts? So the energy is hc over lambda, 1240 EV nanometers divided by 620 nanometers. Why did I pick 620 nanometers? 2 electron volts, right? Because that's half of 1240. So a 620 nanometer photon has an energy of 2 electron volts, and it's red. Let's pick one that's 413 nanometers. Wow, that seems like a random choice, except it's not, because so first of all, 413, what color should that be? Do you think, right? I mean, I'd have to, but
Bluish purple?
yeah, thank you for saying bluish purple. Yes, it's probably like bluish or purple, and don't, no! Yes. So what would its energy be? 1240 over 413 is what, to a good approximation? 3, yeah, because 3 times 413 is 1239, right? So that'd be like 3 electron volts. So notice that on one end you're about 2 eV, on the other end you're about 3 eV. So visible light has photon energies of a little less than 2 to a little more than 3 electron volts. That's something also to remember. Visible light, a little less than 2 to a little more than 3. So about 2 or 3 electron volts, in other words, is a typical energy for visible light photons. Another reason why EV is a convenient unit, right? Why don't we use joules? Because it'd be a frickin' tiny number of joules that you couldn't possibly relate to. Whereas if you do it in EV, well, I don't know what an EV is either, right? But still, I mean, I do, right? But in other words, I can't really visualize how big an EV is per se, but I can compare it, right? And so 2 to 3 electron volts is typical visible light photon energies. By the way, did y'all notice that I gave you back your second homework? So yeah, and one comment I made for a lot of you is the following, and things to keep in mind, right? When we're looking at Halley's Comet, a lot of you answered, and I didn't take off for this, you said its near distance and its far distance, its perihelion and aphelion distances in meters, or maybe kilometers. Who frickin' cares, honestly? Put it in AU. Put it in AU, because you give me it's so many, 10 to the 12 meters, it's like, how far is that? I don't know, but if you tell me it's 35 AU, well, I can't directly visualize 35 AU either, but at least I know it's 35 times further from the sun than Earth, right? So when you're giving distances in the solar system, AU is your go-to unit for distances in the solar system, because then you can compare it to how far Earth is from the sun. Similarly, never, unless I strangely tell you to, never tell me a star's mass in kilograms. I have no idea what 10 to the 33rd kilograms or whatever, or 10 to the 30th kilograms or whatever, I can't visualize that. But if you tell me it's 2.4 solar masses, okay, I don't know how big a I know it's big, right? But 2.4 solar masses is relatable in that it's relative to a standard, the sun. So stellar masses, by default, always put them in terms of the sun's mass in solar masses. Distances in the solar system, put them in AU. Distances between stars, what would you put them in? Not kilometers. I mean, you could, but it's like, what are you doing? Distances between stars should be in? Parsecs. Parsecs are light years, right? Parsecs are light years. Typically, astronomers are more likely to use parsecs. Light years are okay too. But yeah, and remember, let's see, a parsec is about how many light years?
3.26 light.
Well, yes, it's about 3.26, right? So 3-ish, right? So yeah, there you go. All right, excellent. Yes. And electron energies, EV, are our friends here. So, the idea is this particular atom, if it worked out that HC over that energy difference put it in the green part of the spectrum, that harmonium is going to be great at emitting that particular wavelength of green light. That would be harmonium's magic color. Real atoms have multiple energy levels that electrons can transition between, and so they have a whole spectrum, a whole set of spectral line wavelengths. For example, hydrogen, right? Whole series of spectral line wavelengths that are characteristic of it. For hydrogen, there's a lovely red spectral line, a lovely teal spectral line, 2 spectral lines that are arguably something that we will not say, and they blend to the eye to this kind of pinkish color like that. Not a coincidence that if you look at photographs of the Orion Nebula or other so-called H2 regions or emission nebulae, they look this color because they are ionized hydrogen. Ultraviolet light from hot young stars has kicked electrons off of hydrogen atoms. And then, you know, when a proton and an electron come together, they're like, you know what, I'm attracted to you. Well, I'm attracted to you too. You want to get together and make a neutral atom? Yes, you do. And so it'll capture it into some outer orbital, and then it'll drop down the energy ladder. And if it drops from a higher level down to n equals 2, the first excited state, and 3 to 2 is the red line, 4 to 2 is the teal line, 5 to 2 and 6 to 2 are lines of a certain color that we will not name, or at least arguably could be called that, and they blend together with their relative strengths into this lovely pinkish color, is what it comes down to. So I think it's cool that to understand these huge interstellar phenomena, you have to understand tiny little atoms, right? That's one of the things that appeals to me about astronomy. So harmonium, however, a gas of harmonium would be a lovely green color, apparently they have chosen. On the other hand, if I have a gas of harmonium in front of a star, why, I'll see a dark line in the spectrum of that star from the harmonium atoms. Or if I put it in front of a light bulb, why, there will be a dark green, well, if it's dark, it's not green, a dark line that would have been green if only the light were there, so to speak. Because what happens is if you've got a bunch of atoms in the ground state, well, when photons having just that right energy, the energy needed to jump up to E2 from E1, in other words, energy E2 minus E1, those atoms can absorb photons having that energy and jump up to E2 to level E2, and so they remove. So the harmonium gas will remove those photons from the beam, and the light that we get from the source behind it is missing that green wavelength. Not completely, but in other words, there's not as many photons of that green wavelength. Now, of course, we know that those excited atoms are going to do this. They're going to spit out photons again. But the point is, if I've got a beam of light, then what will happen is only occasionally will an atom re-emit a photon into the beam. Usually it'll spit it off in some random direction. And as a result, if you see a hot light source through the gas cloud, it'll be missing photons of that wavelength because they got redirected into other directions by atoms that ate them and then said, "Ugh," and spat them out in some other direction. Does that make sense? Yeah, so that's what's going on there. Yeah. Okay, so here's this idea then, this illustration of, ooh, it's a hot gas of harmonium. I'm so humble. Hot gas of harmonium containing many of these two-state atoms with energy E2, so it's hot. Collisions can also jump electrons up to higher energy levels, and they don't, and with collisions it's different. With collisions it doesn't have to have exactly the right energy to do it. If two atoms collide with more than enough energy to kick an electron from E1 to E2, they can do that, and then it's an inelastic collision. In other words, they leave the collision with less kinetic energy that they entered because some of the kinetic energy was used to promote the electron higher up. So it's not as picky as with photons. So collisions jump some of the electrons into energy E2, and boy, are we going to talk more about how the thermodynamics of that works. And so excited atoms will drop down to the ground state, emitting photons with energy E2 minus E1 in all directions. Why? We put our light collector here, say a telescope, and we take a shaft of that lovely green light, and we pass it through a slit to make a nice narrow shaft of light, which we pass through a prism or a diffraction grating. And so that narrow shaft of green light gets scattered at a particular angle, and we see a spectral line. And the thing to remember about spectral lines is they are images of the slit, right? The reason we see them as lines is because in general with a spectrometer we've passed the light through a slit, and the spectral lines are images of the slit at different wavelengths. Or if you've got a spectrum tube like this, they're images of the tube at different wavelengths. If you didn't have the slit there, it would be all smeared out. So the slit is there so that you get a nice narrow image at different wavelengths of what we call spectral lines. And again, they're lines because they're images of the slit. They're not intrinsically lines They're lines in a spectrum because they are images of the slit at different wavelengths. If it's a continuous spectrum, you've got a continuous smear of images of the slit at different wavelengths. But if only one wavelength is there, which will never be quite true, there'll be some bandwidth, but whatever, shut up, then you'll just get a specific image at a specific wavelength, essentially. What questions do you have? On the other hand, why, if I have a light source producing a continuous spectrum, and so we've illustrated that with, you know, oh, there's red and yellow and green and blue and violet, and fortunately nothing bluish purple there, and really there'd be all wavelengths there, okay, then, ooh, we passed that through our telescope, we passed that through the slit. Again, every wavelength makes an image of the slit, but all the wavelengths are there, and so you get a continuous smear of images of the slit at different wavelengths. You get yourself a lovely rainbow spectrum as a result of that, a continuous spectrum. But now, let's put some harmonium in between the light bulb and our spectrometer. Well, now what happens is that the harmonium selectively eats photons of its beloved wavelength and spits them out in random directions so that the light in the beam headed to the telescope is largely missing that green wavelength because the atoms ate them and spat them out in other directions. We put the light through a slit and we get images of the slit at all the wavelengths except not as much of that particular wavelength is there, and so the image of the slit is darker at that wavelength, and so we get a dark absorption line as opposed to an emission line if it were a hot cloud of gas there. And so we've got an absorption line spectrum where that wavelength is largely missing. What questions do you have? I feel like you're looking at me like you have a question. Am I just imagining it, or you do have a question? Yes.
So, what insight do we draw from the thing that's missing?
That there is a gas of harmonium in front of it. In other words, harmonium has a specific wavelength that it emits and absorbs. In no real atom only has one, but a hypothetical two-state atom which doesn't exist in nature, but if it did, knowing that that wavelength, you know, 547.23 nanometers or whatever it is, seeing that dark spectral line says, oh, there is harmonium there somewhere, because that's what's eating that wavelength. So that's the point, is the spectral lines of an element are kind of like a fingerprint, right? If we're the detectives, ooh, we found the fingerprint of harmonium. That particular wavelength is missing from the spectrum, and so therefore there must be harmonium atoms there that are absorbing that particular wavelength, right? And the big picture is, that's how we know what stars are made of, because we can match up spectral lines with laboratory measurements and determine that those elements are there. And for the sun, and other stars for that matter, we get virtually all the elements in there. There's some exceptions. So for example, element number 43, technetium, it's the rare element that isn't like uranium kind of mass. Technetium is an unstable element. It's not a stable, there's no stable isotope of technetium. And so generally, we don't see technetium in the sun spectrum because any technetium that was created, its half-life is short enough that there'd be none left. Any technetium that happened to be in the sun and was formed, it's all decayed, it's gone. We do see some stars that have technetium spectral lines, and that tells us that there's active nuclear reactions that are producing technetium and being dredged up from the core into the star's outer layers so that we can see the technetium before it all decays away, essentially. Cool. Yes.
So all that is missing is what it's made of.
Yeah, the spectral lines that we see are telling us what's in there, essentially. And so, as we'll see, initially, astronomers figured that the darker the spectral lines, the more light absorption there is, the more abundant the element causing that absorption must be. And it turns out that that plays a role, but temperature plays a more important role. and we'll talk about that. That's how Cecilia Payne-Gaposchkin, Cecilia Payne at the time she did the work, in her PhD thesis in 1925 showed that all normal stars are made almost entirely of hydrogen and helium, even though hydrogen and helium typically are not the most prominent spectral lines in stellar spectra. So an interesting detective story there, which we're going to get to. Okay, what other questions might anybody have? Here's the sun's spectrum. We'll go see that in a few minutes. We won't see it in much detail as that because we won't have a fancy enough spectrometer to do that. But here's the sun's spectrum. It's cut into strips and piled there, right? It would really be all one long continuous strip, but that wouldn't fit on the screen, and so it's been cut into lots of strips and arranged one on top of the other. So it's full of what we call the Fraunhofer lines, after Joseph Fraunhofer, who first observed them in, I think it was like 1814 or something like that. So there's all kinds of dark lines in the sun's spectrum. And again, they're caused by essentially every element, almost every element of the periodic table. We can identify its spectral lines in the sun's spectrum. The element helium, let's see, helium is named after Helios. What is Helios?
The sun.
The sun god, yeah, right, the Greek sun god. Helium got its name because it was discovered on the sun before it was discovered on Earth. They found spectral lines that had never been identified in the laboratory, so there's this new element that's on the sun, and so they named it helium as a result of that. And then later it was identified on Earth. So helium got its name because it was actually first identified in the sun because there was the unknown spectral lines that only later were identified on Earth. Stars typically have an absorption line spectrum. Here is the simplistic picture of it that we will greatly refine, but the basic idea is this. So first of all, on some level, stars are all atmosphere. They're so hot, they're just not solid, right? There's no solid surface on any star. Well, okay, any regular star. There's no solid surface, just a big ball of gas. But we still talk about surface layers. We talk about surface layers of the star, kind of the outermost layers. The sun's photosphere, which we think of it as its surface, is the layer that's only about 700 kilometers, or only about 400 kilometers thick or so, roughly speaking, where photons last scatter before free streaming into space. And so when we look at the sun, it looks like the light is coming from that very thin layer. If you draw a picture of the sun with a pencil, the pencil line that you drew is thicker relative to your drawing of the sun than the actual photosphere is relative to the true size of the actual sun. It's an extremely thin layer. It's the reason the sun looks like it has a solid surface. When you look at it, it looks like it's got a bright solid surface. It's simply because the layer of gas from which we receive the light, the photons are last coming from that layer before it's free streaming out into space. It's so thin compared to the sun's size that it looks like a nice sharp boundary, even though that's really just an illusion. It's really fuzzy. But the angular resolution of our telescopes at the sun's distance is like 700 kilometers, and this layer isn't as thick as that. So you can't tell the difference between that and a nice, truly sharp boundary. Anyway, the idea is that the deeper you go inside the sun, the hotter it gets, and the denser it gets. So below the photosphere, the gas is hotter and denser, and as a result produces essentially a Planck continuous spectrum, a nice hot rainbow continuous spectrum. There's a relatively thin layer of gas that's cooler, not cool by human standards, right? In other words, oh, it's only 5,800 Kelvin. It's a frigid, like 10,800 degrees Fahrenheit. Okay? But it's cooler than that stuff below, that other stuff below. It's even hotter. And the idea is that, in other words, the sun's outer surface layers act like in relative terms, cool cloud of gas in front of a hot light source. The hot light source being the deeper, hotter, denser layers below, producing a rainbow of colors, but the cool cloud of gas, the surface layers, selectively absorb some of the light, and as a result, wavelengths are missing, and we see an absorption spectrum. That's why stars generally have an absorption line spectrum, is that the cool upper layers of the star, the atoms there, absorb light from the hotter source of continuous spectrum below, and so we see an absorption line spectrum. There are some exceptions. Some stars have hot outer atmospheres that produce emission lines, and the sun has, in a layer called the chromosphere above the photosphere, which is hotter than the photosphere, the hydrogen there produces emission lines. And so you can have an H-alpha telescope where you have a filter that selectively only passes the hydrogen alpha spectral line, the deep red lovely spectral line of hydrogen, and doesn't let through other wavelengths. And when you do that, you see the chromosphere, and it's beautiful. You see prominences, you see filaments, you see, and so on and so forth. So why, if you took advantage of Don Stevens having the solar telescope out there at the Connection Conference, you too could see those lovely things. And if you haven't seen it, I'll probably borrow it at some point so we can look through it, because it's freaking cool. And it's also the little licks of flame you see at a total eclipse. That's actually the chromosphere. You're seeing hydrogen alpha, 3-to-2 transitions in hydrogen, illuminating hot gas suspended by magnetic fields above the photosphere. Go to your other class. Get out of here. Leave. Bye. And we'll take a break at this point. All right, so the joy of solar spectral lines, dark lines. If you're joining us remotely, just come and talk to me and I will give you a private demonstration of these solar Fraunhofer lines that we just saw using these glorious Project Star spectrometers. You too can join me and see them for yourself. It's really cool. Okay, now, reminder, simplest element, hydrogen. If you study it using the Bohr model, which doesn't deserve to work, but it does magnificently, I always say, if it were obvious to me that the Bohr model, which is a semi-classical model, where the electron moves on a circular orbit around the nucleus, would give the same energies as the Schrodinger equation does, if that were obvious to me, if I could look at that and say, well, of course, you're going to get the same energies out, I would be a much bigger, smarter, geniuser person than I may be now. I mean, it's just like, it doesn't deserve to work. It's like a miracle, and yet it does. The math works out. Either using the Schrodinger equation or using the Bohr model, we find that there's what we call, right, the principal quantum number that we can label the energy levels with. And you get this fancy expression that is a bunch of stuff minus a bunch of stuff divided by n squared as the energies of the orbitals. It's the actual energy of the orbits in the Bohr model. It's the energies of the orbitals when you do it with the Schrodinger equation. And relative to 0 being the electron and the proton are at rest at infinite separation, calling that 0, the energy levels are minus 13.6 electron volts divided by n squared. Is that ringing a bell? Do you remember that sort of beast? Okay. So let's look at that then. So here's an energy level diagram then for hydrogen. The ground state is called n equals 1. The principal quantum number is n equals 1 then. So the energy of the ground state relative to 0 at infinite separation at rest, relative to that, is minus 13.6 electron volts over 1 squared. Quick, what's that equal to? minus 13.6 electron volts, as a matter of fact. So you can see that on the scale. Here's this from your book, this figure. Minus 13.6 electron volts. And then you go to E2, it's minus 13.6 electron volts over 2 squared. 13.6 over 4 is 3.4. So that's minus 3.4 electron volts. So the first excited state is up here at minus 3.40 electron volts. E3 is minus 1.51 electron volts, 13.6 over 9. E4, 13.6 over 4 squared, 13.6 over 16, minus 0.850 electron volts. E5, minus 0.544 electron volts. Notice that as you go to higher and higher n values, the energies are getting closer and closer together, and in the limit, as n goes to infinity, what's minus 13.6 divided by infinity? 0, right? So it asymptotically approaches 0 electron volts, which means that from the ground state, the ionization energy, the minimum energy needed to remove the electron, is 13.6 electron volts. If you give it more than 13.6 electron volts, the electron will have kinetic energy left over after you detach it from the nucleus. But if you give it the minimum energy such that they're separated at a large distance, technically infinite, they're separated at a large distance and classically speaking, at least at rest with respect to one another, that would take 13.6 electron volts. But what if a collision kicked it up into the n equals 2 level and you wanted to ionize it from there? What's the minimum energy that would be needed to ionize from the n equals 2 level? 3.4 electron volts, because n equals 2 has an energy of minus 3.4 electron volts. Ionization with no kinetic energy is 0 electron volts. So 3.4 plus minus 3.4 would take you up to 0 energy. Far separation, not moving. So the ionization energy from the n equals 2 level is 3.4 electron volts. From the n equals 3 level, it only takes 1.51 electron volts to ionize it, etc., etc., etc. And again, on the energy rungs here, n equals 1, n equals 2, n equals 3, 4, 5, 6, 7, 8, infinity is at 0, and they just get closer and closer together, the energy levels from there. In intro astronomy, the students often say, why do the energy levels get closer together? And I basically say, because Schrodinger equation. It just does. You know, I don't know how to make it intuitive. The Bohr model, the Schrodinger equation, they both say the energy levels get closer and closer together. Why? Do the math. I don't have an intuitive explanation for why they do that, but they just do, because math. Meanwhile, we can talk about possible transitions of electrons from one energy level to another. And so we talk about series of spectral lines. And so the Lyman series, often abbreviated LY like that, are all the transitions to and from n equals 1 as the lower of the two levels. So in other words, a transition from n equals 1 to n equals 2 in either direction. It's emission, if it's 2 to 1, the electron's dropping down in energy and giving off a photon. It's absorption, if it's 1 to 2, the electron is absorbing a photon and using that to jump up from n equals 1 to n equals 2. That's called the Lyman alpha line. We give them Greek letters, where the lowest energy in the Lyman series is Lyman alpha, 1 to 2, either way. Lyman beta is 1 to 3. Lyman gamma is 1 to 4. Lyman delta is 1 to 5. What would Lyman epsilon be? 1 to 6, and so on and so forth, right? And so we have a whole series of spectral lines. Lyman alpha, does it have the longest or the shortest wavelength of the Lyman series? It's the lowest energy, so that it has the longest wavelength or the shortest wavelength. The longest wavelength of the entire series is alpha, and then the next longest, second longest is beta, third longest is gamma, and so on and so forth. in terms of energy, the lowest energy is the alpha line, second lowest is the beta line, third lowest is the gamma line, right? So in terms of wavelengths, longest, shorter, 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 get shorter and shorter and shorter, the energies are getting larger and larger and larger because a photon, the shorter the wavelength, the higher the energy. So what is the energy of a photon absorbed or emitted in a Lyman alpha transition? How would I calculate that from the numbers here? What is the energy of the Lyman alpha transition? So if you absorb it, it needs to have enough energy to go from n equals 1 to n equals 2. How much energy is that? What energy does it start with? Minus 13.6. What energy does it end with? Minus 3.4. Is minus 3.4 more or less than minus 3.6? It's more, right, because it's negative, right? So the smaller the negative number, the larger it is, algebraically speaking, right? Minus 3.4 is greater than minus 13.6. Not in magnitude, but in, so, right? So I have to give it how much energy. It will be E2 minus E1, minus 3.4 minus 13.6, right? So in other words, its energy is 13.6 minus 3.4. How much is that?
13.2.
It's 10.2, right? 10.2 electron volts. So the Lyman alpha line is 10.2 electron volts. Having gone through that, let's make the calculation suddenly easier. 10.2 electron volts. So you can also, where you call the zero of energies arbitrary, we will always consistently say the zero of energies when they're far apart and not moving. But it makes things easier for quick calculations if you call the ground state 0 electron volts, right? You're just shifting all the energies. And so this labels how high each of the other energies are above the ground state. Right, so n equals 2 is 10.2 eV above the ground state. So the Lyman alpha line is a 10.2 electron volt photon. Is that in the visible range based on that energy? What's the visible range, roughly speaking, for EV? 2 to 3-ish. Is 10.2 in that range? No. Is it more energetic or less energetic than visible light photons?
Less.
Wait a minute. 10.2 electron volts, so I'm talking energy here, not wavelength.
Oh.
Energy, right? Much higher energy, therefore the wavelength is less. So that's an ultraviolet spectral line is what it comes down to. Lyman alpha, if I take 1340 and divide it by 10.2 electron volts, it's about this. These are more precise using the actual value of HC. But essentially, if you take 1240 EV nanometers and divide it by 10.2 EV, you get, close enough, 121.6 nanometers from that. Again, if you put it in your calculator, I think it won't be quite that because 1240 is an approximation. And this is out to 4 sig figs here. So put in the actual value, 1239 point whatever it is, blah, blah, blah. 121.6 nanometers, that's definitely an ultraviolet photon. And that is the longest one. So are any of the Lyman alpha, are any of the Lyman spectral lines visible spectral lines? No, because Lyman alpha is the least energetic, longest wavelength one. So all the other ones are more energetic and shorter wavelengths. So that's even worse. They're further and further into the ultraviolet. So Lyman beta, 102.6 nanometers, Lyman gamma, 97.3, Lyman delta, 95.0, and so on and so forth. In principle, there's an infinite series of spectral lines here, although they tend to a limit. They tend to a limit of whatever 13.6 electron volts would be kind of, the last infinite line. There's no last line in the series, but also you can't really have an atom where it's in n equals 5,000 or something like that. It would be too large and unstable. Anyway, that's the Lyman series of lines. The next series, where it's to or from n equals 2, and know this is so important, it shows up all the time. that transitions to and from n equals 2, but no lower. In other words, the series is based on the lower of the two levels. So the Balmer series are transitions to and from n equals 2, named after a high school teacher, Balmer, and he's the one that found the empirical formula for their wavelengths that then Bohr was able to reproduce with this Bohr model. So Balmer alpha is the 3 to 2 transition, right? So it would be 3.40 minus 1.51 electron volts. Balmer beta is 4 to 2, Balmer gamma is 5 to 2, Balmer delta is 6 to 2, and so forth. Epsilon would be 7 to 2, and so on and so forth. When you run the numbers, you get that Balmer alpha, the 3 to 2 transition, is 656.3 nanometers and is a lovely red spectral line. Why, I'll bet you saw it earlier today when we turned on the hydrogen lamp. Balmer beta is a 486.1 nanometer line. It's a lovely teal color. Balmer gamma is 434.0 nanometers. Balmer delta is 410.1 nanometers, and I find I can't really see it from the tube. I can see the first three. In a more professional kind of spectrometer, I can see the delta line. Epsilon is a little bit into the ultraviolet, and so you don't see any of the other Balmer series lines. They're in the near ultraviolet, the very near. On the other hand, if you get cataract surgery, maybe you'll be able to see some of those too, right? Reasons to ruin your lens? No, not really a reason to. So anyway, those are the Balmer series lines. They are 3 to 2, 4 to 2, 5 to 2 transitions in hydrogen. Those are the visible spectral lines of hydrogen. Can't emphasize that enough. The visible spectral lines of hydrogen are the Balmer series spectral lines. Meanwhile, you know, if you really want to pursue this a lot, you might feel very passionate about it, because why, you could even look at the n equals 3 to other level transitions other than 2 and 1, right? It's 2 and from, n equals 3, but no lower. 2 and 1 aren't considered because those are already in the alpha, in the Balmer and Lyman series. So there's the Paschen series of lines, and they're all in the infrared. They're all too low in energy to be visible light photons. And bonus points, I know what the next two are called. So if you go from level 4 to some higher level, to or from some higher level, you got Lyman, level 1 to some higher level, to or from a higher level, Balmer, level 2 to and from some higher level, Paschen, level 3 to some, to and from some higher level. What about 4? Anybody know what that one's called? It turns out it's the bracket series. And then n equals 5, that's the Pfund series, P-H-U-N-D. Once I had Kirsten Pfund as a student, and she rather enjoyed the fact that there was a series named after her. On some level, as I like to say, you know, there's an infinite number of n values, and so you can just pick some large value of n and nobody's used it before and name it after yourself, right? You know, so there you have it, right? Nobody else is going to call it that, but you personally can decide that that's your series of radio wave hydrogen spectral lines, if you like. What questions do you have? All right. Okay. Now, we need to go to, we need to know a bit more here in order to go to the next level, because what we're going to do is talk about the thermodynamics of the populations of energy levels in thermal equilibrium. In other words, if you have a bunch of hydrogen gas and it is at a certain temperature, what fraction of the hydrogen atoms are in the ground state, n equals 1? what fraction are in the first excited state, n equals 2, what fraction are in n equals 3, and so forth. We're going to develop the Boltzmann equation, which describes, in thermal equilibrium, the populations of all of the different energy levels, what fraction of atoms are in each energy level, depends on the temperature. At very low temperatures, everybody's in the ground state, essentially. At absolute zero, everything would be at the ground state. As the temperature rises, a larger and larger fraction of the atoms are in the first excited state, or the second excited state, and so forth. We won't derive it, we'll give the equation that describes that and give it some intuitive justification. And we'll also talk about the Saha equation after a famous Indian physicist who was able to come up with the populations of different ionization states. What fraction of the hydrogen atoms have had their electrons stripped from them? Or if it's carbon, how many electrons does carbon have? Do you remember? Carbon is which element? 6. So for something like carbon, which fraction, it depends on the temperature and other things too, but mostly the temperature, what fraction of the carbon atoms are neutral? They've got all 6 electrons. What fraction are singly ionized? They're missing 1 electron. What fraction are doubly ionized? They're missing 2 electrons, and so forth. We need to know those things for all the different elements to know how many examples of doubly ionized carbon atoms there are to produce the spectral lines of doubly ionized carbon in a star, for example. So that's our big picture here, is we want to know how to use the Boltzmann and Saha equations to predict the population of the atoms that will be in a given energy level for a given ionization state, and use that to gain insight into how strong the spectral lines will be for given elements and given spectral lines, given energies of the transitions. So we are going to, it turns out, need to know, first of all, what are the energy levels relative to the ground state? In other words, I need to know if I want the population of electrons in n equals 3 for hydrogen, turns out, maybe not too surprisingly, you need to know how much energy it takes to go from the ground state, where everybody would be at low temperatures, to kick it up to that n equals 3 level. But another thing you need to know are the so-called degeneracies of the different states, where the degeneracy is, do you remember what degeneracy is in quantum mechanics? What does degeneracy refer to? Not sociologically, right? When I was in grad school, my sister and I both liked The Cure, and so my sister was up in Chicago, and we went to see The Cure in concert, and my lovely wife had no particular interest in seeing The Cure, not her thing, so she didn't want to spend money on a ticket. She was my fiance at the time, but anyway, or no, she was still just my girlfriend at the time, my future fiance and wife. Anyway, so she had the car, so she drove us to the concert and stayed outside. And she had a conversation with, it turns out, an Indian gentleman who had brought his daughter to see the concert. And the content of their conversation was largely how he thought that The Cure and their fans were largely a bunch of degenerates. And so that is not the meaning of degenerate that I'm talking about here. Do you remember what degeneracy is in quantum mechanics? And I don't mind being called a degenerate. I was told, I'm kind of like, cool. I liked it. But anyway, what is degeneracy in quantum mechanics? It refers to multiple quantum states having the same energy. So remember with hydrogen that, to a really good approximation, it's not true strictly speaking, but to a really good approximation, the energy levels depend only on the principal quantum number n, and not on the other quantum numbers that could describe the electron in a hydrogen atom. Do you remember what those other quantum numbers are? There's a set of 4 quantum numbers that describe the electron in a hydrogen atom. There's the principal quantum number n, which determines kind of the overall orbital it's in. Think back to your chemistry. 1s, right? Right? 2, what? 2s, and also 2p. 3s, 3p, 3d, 4s, 4p, 4d, 4f, right? So we've got s, p, d, f, g, h, right? All of a sudden they decided to be reasonable, right? So even physicists can have weird names for things that basically happen because they didn't know what was going on at first. S, P, D, and F stand for the character of the spectral lines. They stand for sharp, principal, diffuse, and fine. And then they're like, okay, let's just start saying G and H and stuff like that after that. Do you remember what S, P, D, F, and all that, what do those refer to? What property of the electron do those refer to?
Isn't it about how many of them are isolated?
No, it's not. So even for just a single electron in a hydrogen atom, you've got the orbital energy, and that's largely determined by n. And then there's also, let's see, while it's not a classical particle literally revolving around the nucleus. If it were, it would have orbital, yes, angular momentum, yeah. S, P, D, F, all that refer to the orbital angular momentum of the electron. So S, right, jog your memory here, corresponds to little l, the orbital angular momentum quantum number equals 0. P refers to little l equals 1. D refers to little l equals 2. F refers to little l equals 3. G is 4, blah, 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 blah. So you've got the orbital angular momentum quantum number that we can either give letter names or just values. But wait, there's more. There's also the z component of the orbital angular momentum, and that's described by a quantum number m sub l, sometimes just called m, but it's better to say m sub l. And so the electron could have, it's in n equals 2, but it's a p state, so L is equal to 1, and if L is equal to 1, what can m sub L? I'll systemize this in a minute, but I'm just trying to jog your memory, see what you remember. If little l is equal to 1, what could m sub L be? Minus 1, 0, or 1, right? It goes from minus L to L in steps of 1. And then there's one more piece. Not only does the electron have orbital angular momentum, it also has what other kind of angular momentum? The mysterious spin angular momentum. And it's an intrinsic spin angular momentum that can't be changed, described by a quantum number little s is equal to 1/2. And m sub s, describing the z component, can be plus 1/2 or minus 1/2. In other words, the electron can be, quote unquote, spin up or spin down for the z component quantum number. And so, to completely specify the state of an electron in a hydrogen atom, I need to know n, l, m sub l, and m sub s, 4 separate quantum numbers. And again, to a really, really good approximation, the energy only depends on n, and any electron with the same n but a different value of L, m sub s would still have the same energy. In other words, there are multiple quantum states that have exactly the same energy because there's 4 quantum numbers that characterize the electron fully in terms of its energy and angular momentum. But in hydrogen, it doesn't care about those in terms of the energy. So those are degenerate states. They all have the same energy, and we can talk about the degeneracy, the number of states that all have the same energy. In multi-electron atoms, because of electrons interacting with one another, it turns out that m sub l does play a role. So in a single electron hydrogen atom, 2s and 2p have the same energy. 3s and 3p and 3d all have the same energy. But in a multi-electron atom, you will recall, 2s has less energy than 2p does by a little bit, and 3s has less energy than 3p, has less energy than 3d, but things get complicated when you get like 4s, because then you start having shells being inside of periodic table stuff, right? All that business. But we need to talk about then degeneracy, because the population of the levels depends on how much energy it takes to get them into those excited levels. But the more degeneracy there is, the more atoms will be at a given energy level, because in a sense there's more ways to get the atom into that energy level. And so we'll see that the degeneracy plays a role too. When we write it down, it'll start to sort itself out. Reminder, we've already done this, right? Spherical coordinates, right? In the proper physics way, right? None of that silly calling theta phi and phi theta that those silly mathematicians do, right? So there's your spherical coordinates there. And how many of you have had physics 380 already? So some of you, and then some of you have only had 280 so far. If you had it from me, I just said, well, here's the wave functions, and we're not going to worry about how we got them. So you might have seen this before. The electron in a hydrogen atom, and roughly speaking, didn't mean to do that. Roughly speaking, in a multi-electron atom as well, although it's not as good an approximation in a multi-electron atom, we can describe the wave function with a series of quantum numbers. So we got psi NLM in spherical coordinates as a function of r, theta, and phi, giving the probability density of finding the electron at a given place, right? It's psi star psi will be the probability of finding the electron at a given location, or near a given location, and it breaks down into RNL of R. In other words, this function that depends only on the radial coordinate, the distance from the center, and the functions are labeled by two quantum numbers, n and l, and then there is YLM of theta and phi. So that's labeled by the two angular momentum quantum numbers L and M. These are the same L that are showing up there. And those are called spherical harmonics. And so the wave function is going to be a product of one of these RNL functions here. Like, for example, R31 is the radial function when n is equal to 3 and L is equal to 1, and it's equal to, obviously, 8 over 27 times the square root of 6 times the Bohr radius cubed times r over the Bohr radius times 1 minus r over 6 times the Bohr radius times e to the minus r over 3 times the Bohr radius, right? I mean, you remember that, right? I don't. Right? I look them up if I need them. Come on, give me a break. So there's all these RNL thingies times one of these spherical harmonics. So they're just functions, right? You can look them up. They seem kind of scary, but when you look at them, they're not that scary. Y21 is minus the square root of 15 over 8 pi times sine theta cosine theta e to the I phi. It's just these functions that you can look up. Solving form is a little bit more involved, but you can look up these functions. And so the different states that the hydrogen atom can be in are described in the end by three quantum numbers, N, L, and M. And if I tell you what they are, and then there's also, that's the spatial wave function, and then there's also a spin wave function, the electron. So each one of these spatial wave functions, like for example, a 3p state that has a certain value of M, if there's one hydrogen, if there's just one electron around, okay, well, the electron can have all this. But if you're in a multi-electron atom, how many electrons can go into any given spatial state, any given orbital? At most, how many electrons can share the same orbital? Two, and their spins have to be related in what way?
Opposite.
Opposite, right? So one's got to be spin up, if you will, the other spin down. That's an extra degeneracy as well. The electron can be spin up or spin down in a given orbital. If we're just looking at hydrogen then, if we want the degeneracies, we have to count up for any given value of n, how many L, M sub L, and M sub S values could there be to go with it? Here I haven't labeled this as M sub L, I've just left it as M, but if I'm worried about spin 2, sometimes we'll say this is M sub L, although usually when we write YLM, we just leave it as M, and if we want the spin, we'll be like M sub S. We might just leave this as M and not M sub L. It's up to us. It's whatever we friggin' want to do is what it comes down to. Okay, so let's remind ourselves what the rules are, and then we'll continue this next time. So because we still have a few minutes, that's a little fast, right? So what are the possible values? So the quantum rules for electron in atom. The principal quantum number n, what values can n take? What's the smallest value of n? Yeah, 1, right, 1. And what's the next value that it could take? 2, 3. In principle, is there any limit? No. So in other words, n is just a positive integer. That's the rule for n. It could be anything in principle. It's a positive integer. And remember that for hydrogen, except for when you account for spin-orbit interaction, all these subtle effects, to an awfully good approximation, the energy is this minus 13.6 electron volts over n squared. That's the one that determines the energy. You got the orbital, I'm not aware of a good short name for this, orbital angular momentum quantum number L. So what's the rule for L? Do you remember? Well, we know if it's, and I'll remind you here that for L, it's probably not on camera, for L, S states are L equals 0, P states are L equals 1, D states are L equals 2, etc. It goes like that. So let's see. Can you have 1p? Nope, you have 1s. Can you have 2s? Can you have 2p? Can you have 2d? No, right? Etc. So in other words, it's 1s, 2s, 2p, 3s, 3p, 3d. So if you think about that, what that's translating to is L goes from 0, can I erase this bit right here? L goes from 0 to n minus 1 in steps of 1. So if n is 1, L can only be 0, 1s. If n is 2, L can be 0 or 1, 2s, 2p. If n is 3, L can be 0, 1, or 2, 3s, 3p, 3d, etc. So the rule for L is it goes from 0 to n minus 1 in steps of 1. So if n is 7, what are the possible values of L? 2, 3, 4, 5, stop at 6, yes, so on and so forth, right? That's the rule. And then we got the Z component of, good God, there needs to be a smaller name to this. The Z component of orbital angular momentum quantum number. I don't know if there's some more compact name for this. Z component of orbital angular momentum quantum number quantum number. We'll call it just M here. We sometimes would call that M sub L. So what's the rule there? So if it's a p state, right, how many p orbitals are there? For S state, there's only one. For P states, there are how many? Not a peace sign. Got to get a little more. 3. Yeah, there's 3. Yep, 3 of them. Yeah. And in terms of M sub L or M, we say -101. For a D state, how many are there? 5. So M sub L, or just if we call it M, is -2, -1, 0, 1, 2. So in other words, M, or M sub L, goes from -L to L in steps of 1. So there's 1 S state, 3 P states, 5 D states, 7 F states, and so on and so forth, because, right, if you count them up, D states, -2, -1, 0, 1, 2, that's 5. So that's how that works. And then finally, for the spin, M sub S can only be plus or minus 1 half, plus or minus a half. So for the spin, you get a factor of 2 in the degeneracy, because it can be spin up or spin down in terms of the quantum number. Right. And so it's time to go. It's a little past time to go, but I'm giving you some free extra education. You're welcome. I won't charge you for it. We will discover that the degeneracy is 2n squared. That's how it works out. 2n squared. For example, for the ground state, you've only got one s, but there can be spin up or spin down electrons, so that's a degeneracy of 2. 2 times 1 squared is 2. The electron in the ground state can be spin up or spin down. That's the degeneracy, same energy. For the 2s and the 2p together, there's 1 2s state, 3 2p states, so there's 4 n equals 2 states altogether, 1s and 3p states. And each one of them can have the electron either spin up or spin down. So there's 8 ways to put the electron in the n equals 2 shell. And 2 times n squared, 2 times 2 squared is 8. It worked out. And it'll keep working out. 2n squared is the degeneracy. And we'll need to know that as part of the so-called Boltzmann equation. It's going to be great. And we'll do that next time. He said, dropping the, not Mike, dropping the meter stick. I said it's the week of, so actually we need to talk about that. We'll decide. Yeah, I forgot to mention that today, stupid. Any idea of when you would like to have said exam?
Not Wednesday.
Not Wednesday, you say?
I have a midterm on Wednesday.
Oh, you have a midterm on Wednesday. What's that? Monday? Yeah, you want it on Monday? We should have everybody here before we decide such a thing.
It's going to be 2 hours long?
I probably would just do it in the evening so it can be longer than that, so you can have more time than just 2 hours. And I'm not going to try to make it 5 hours long, but you know.
We'll talk about like what's going to be on.
Yeah, I will put out a review guide.
Okay.
Yeah. So basically, you know, homework plus be able to explain these concepts, because I do put some like essay questions on there, because we're telling, we're not just doing equations, we're telling stories, and I want you to be able to tell stories about what these things mean and so
I'll
forth.
just start setting the first two homeworks tonight, data and start.
Yeah, and I'll get the third one graded and post those, and essentially, this stuff won't be on it, because we're not going to do a homework on it before then. It breaks my heart, but I didn't give you an assignment also for last week, for this week or whatever. Partly because
Do this upcoming week.
there's nothing due this week. There's just nothing, because I figured it's exams next week, so, yeah.
I'll spend the time over doing homework on that, so.
Yeah, there you go, exactly, yes, seems like a strategy.
So if I
Yes.
fail, I have no excuse.
That's right, you're damn right, that's right, yes.
Normally I would, but
Yeah, but this time, no, yeah.
So it's gonna be closed books and everything, right?
Yes, it'll be closed book, but you don't have to memorize formulas. I will give you a formula sheet, and you just have to know, how do I use this, essentially, yes.
You know, I wanted to talk to you about this, because the first two chapters, they're just really complex when it comes to using formulas.
Yep, there's a lot in there, that's right,
And they all are like several ways to represent one thing. So I've always wanted to ask you, like, how to get this right for the exam. Because for homework, you have a lot of time, and you can sit for exam.
Right.
I'm afraid I'd mess up.
Well, I hope not, and one thing that has to be said is that on an exam, I don't intend to give you a complicated derivation, because it's just not realistic to do that. Exam problems can't be as involved as homework problems are, so I will say that. And when I put out the review guide, have a look at that. That might give you some insight about what should you ask about possibilities on the exam. So, yep. Yep.
Because I think my office is occupied. My office might be occupied.
Right back here.
Isn't the thing for football?